Hi everybody. So this is my second video on modeling with forced harmonic motion. In the first video, I showed you how forced harmonic motion is different from damped harmonic motion. In this video, we're going to look at how we can set up the differential equation by considering the different forces. So we're told that a particle of mass 1 kilogram moves along the x-axis. And at time t, the displacement of q from the origin is x meters and the speed of q is v meters per second. We're told that three forces act on q. There's a restoring force, a resistance to the motion of q in terms of v, and a force of magnitude 6 cos t acting in the direction of O to q. We're told that q is initially at rest at the origin, and we need to set up this differential equation. So the first thing I'm going to do is start by sketching a diagram. We have the x-axis, and we'll say this is the origin, and that q is moving along the x-axis. So I'll place q here. And the direction of motion will assume to be positive in this direction. So we're told that the three forces act on q. There's a restoring force of magnitude 5x. Now the restoring force will always bring q back to the equilibrium position. So if this is positive, the restoring force will be acting in this direction because it's bringing q back to the origin. And this has magnitude 5x. Then we're told there's a resistance to the motion of q of magnitude 2v. Again, if q is moving in this positive direction, then resistance is acting against the motion. So resistance will be acting in this direction. And we're told this has magnitude 2v, where v is the velocity. And then we're also told there's a force of magnitude 6 cos t acting in the direction O to q. And O to q is acting towards the right. This will be the driving force of magnitude 6 cos t. So we know that q is moving in this direction, so there must be a net force. And the net force is found from F equals ma. So if we resolve our forces, we have the restoring force, which is a negative. We have the force due to resistance, which is also a negative. And then we've got a positive driving force. And this will give us a net force of ma. We're told that the mass is 1, and the acceleration is d squared x over dt squared. We can see the restoring force is already in terms of x. The velocity we can write as dx over dt, and then we've got the driving force in terms of t to give us our net force. So now to make this look like the equation we have here, we'll move all the x terms to the right-hand side. So we'll have 6 cos t will equal d squared x over dt squared plus 2dx over dt plus the 5x. And that's what we're asked to show here. So this is how you set up your differential equation by resolving each of these forces. And now for part B, we need to find a particular solution for this differential equation. And now we can set up our auxiliary equation. We'll take the coefficients from our left-hand side. So we'll get m squared plus 2m plus 5 equals 0. When we solve this, we get complex solutions. M will equal minus 1 plus or minus 2i. So our complementary function will have x is equal to e to the power of our real part, negative 1, multiplied by a times the cos of 2t plus b sine of 2t. So that's our complementary function. But because there's this driving force, we need to think about a particular, and this will be in the form that matches this driving force of 6 cos t. So we'll have x equals a constant lambda times the cos of t plus a different constant mu times the sine of t. We always need to check at this point that the term in our particular solution doesn't match a term in our complementary function. If it did, we'd have to times each of these by the variable t. But you can see they don't match, so we're good. We have a dx by dt term, so we'll find dx by dt. This will give us negative lambda sine t plus mu times the cos of t. And then we'll find d squared x over dt squared. This will give us negative lambda cos t minus mu sine t. And then we'll substitute each of these back into our differential equation. So if we substitute this into here, and we add 2 lots of dx by dt, we'll expand out that bracket. So this will become minus 2 lambda sine t plus 2 mu cos t. And we'll substitute the x term into here and expand that with 5. So we get 5 lambda cos t plus 5 mu sine t. And this will equal the right-hand side, which is 6 cos t and 0 sine t. So if we identify the cos t terms separately to the sine t, then we can equate the coefficients. So we've got cos t negative lambda plus 2 mu plus 5 lambda plus the sine t negative mu minus 2 lambda plus the 5 mu. So if we collect the like terms here, we know this will equal the coefficient of the right-hand side, so this will equal 6. So 4 lambda plus 2 mu will equal 6. We'll do the same for the coefficient of sine t, and this will equal 0. So negative 2 lambda plus 4 mu will equal 0. And then we can solve these simultaneously to work out lambda and mu. Lambda will equal 6/5, and mu will equal 3/5. Now we can substitute these constants back into our particular integral here. We'll have 0 is equal to, this will become e to the 0, so just 1. This sine term will become the sine of 0, so this will go, and the cos of 0 will become 1, so we'll just have this a term. The cos of 0 again is 1, so this will give us 6/5, and this term will also become 0. So therefore, a must equal negative 6/5. And then to work out b, we'll replace this a with negative 6/5, and we need to differentiate x to use this initial condition. So dx by dt, using a product rule here, we'll let this equal our u term, and this will be the v term. So we'll have u times dv. When we differentiate this, we get 12/5 sine 2t When we're differentiating this, we get positive 2b cos 2t plus du. When we're differentiating this term, we get negative. So negative e to the negative t multiplied by the v term. We'll differentiate this and we get negative 6 over 5 sine t. When we differentiate this, we get positive 3 over 5 cos t. So I don't need to expand out these brackets, we can just substitute in these conditions. We know dx by dt is given as 0. When t is 0, this will become 1. This term will go, so we're just left with 2b. This will become negative 1. The cos term will become 1, so we get negative 6 over 5. The b term will become 0. So will this term, and this will become positive 3 over 5. So I'll close that bracket and we'll add 3 over 5. So we'll get 0 is equal to 2b plus the 9 over 5. So therefore, b will equal negative 9 over 10. And now we can substitute this value for b back into here. So b will become negative 9 over 10. Okay? And this is the particular solution. X as a function of t. So now for part C, describe a motion when t is large. Well, we can say that when t tends to infinity, then this term, which we can write as a fraction, 1 over e to the t, this will tend to 0. Because when we divide 1 by this very large number, it will tend to 0. So if e to the negative t becomes 0, all of this becomes 0. So what we're left with is this bit. So when t tends to infinity, x will tend to 6 over 5 cos of t plus 3 over 5 sine of t. And the question is, what will this tend to? Well, we can write this using the harmonic formula. This is when we have r multiplied by the sine of t plus alpha. We know alpha will be the arctan of the sine term divided by the cos term. So alpha will tend to 0.463 radians. And r will be the square root of 3/5 squared plus the 6/5 squared, which works out as 3 root 5 over 5. So we'll say that when t is large, x will tend to 3 root 5 over 5 meters away from the origin. Okay? Well, thank you very much for watching. I hope that's given you a clearer idea on how we can set up and solve differential equations using forces. If you want more practice on this, you can download the worksheet and view the online lesson from my website. I'll leave a link in the description below.